Welcome, dynamics students. This problem is the first in our rigid body planar kinetics. And this problem is interesting because it looks so much like what we're probably all used to from statics, and it requires us to really step out of what we would have considered our comfort zone if we were in statics class. So in this problem we have a crate, and it's kind of supported on a couple of little feet on a surface. We've got a center of mass and a crate weight of 150 pounds here, and we've got some dimensions. Basically the crate's probably uniform in density. Make sure we're all seeing the same thing. We have some dimensions, 1 foot to either side here. The center of mass is 3.5 feet, 3.5 feet above the surface where the normal force can react on it. We'll call this point B and point A. And I'm actually doing an FBD right from the schematic. Not necessarily recommended, but it is a very simple schematic in this point, so I can get away with it. So I have a force that someone's pushing on the crate, 35 pounds, at a height of 4 feet above the ground surface. Okay. And then the crate's rigid, and I guess we can assume let's slap a coordinate system down here in case we need to keep track of our signs. And somebody asks us, what is the acceleration of the crate? It's going to accelerate sideways, and let me just draw like a little indicator to show it's on a rigid surface, so it's not going to sink down into the surface. So we need to know what is the acceleration basically of the center of mass of the crate. And somebody wants to know what the magnitude of the reaction forces A and B are holding up the crate. So if this were in static equilibrium, this would be easy. We'd take the sum of the moments about 1 point, and we'd take the fact that that it isn't moving in any direction. We can relate frictional forces. We're done. But this is a dynamics problem, so we can't assume the sum of the forces in the x direction is 0. In fact, given the fact that somebody wants to know what the acceleration is, we can pretty much assume it probably isn't. Okay, so I'm going to go ahead and draw a nice FBD over here because I don't have the frictional forces. So I'm going to FBD the crate, which is really other than the coordinate system, which I'm going to repeat over here. Establish your coordinate system, which in this case, let's go ahead and remind ourselves that that's the direction of positive rotational acceleration in case we need it. Looks like this may end up being a translational problem, but now we know. We'll remind ourselves that that's 3.5 feet. This is 1 foot, 1 foot. We've got 35 pounds, 4 feet, and I'm going to go ahead and use some different color here to make it a little easier. We've got normal force A and normal force B, and then we've got frictional force A which, just like the case for statics, will be opposite the direction of motion or imminent motion. And we've got 150 pounds going down. Okay, so we can go ahead and sum this. We can say the sum of the forces in the x direction is, given our sign convention, going to be 35 pounds. Positive minus f sub a minus f sub b. All of that is going to equal, we don't need this schematic anymore. I can just move this over here. All of that is going to equal the mass of the crate times the acceleration of the crate's center of mass in the x direction. And we can remind ourselves that m crate equals 150 divided by 32.2 approximately slugs, the British mass unit. So here's our acceleration expression. We can simplify this probably because we can relate some things about frictional force to our normal forces, so that's something else we can do. But we have our fundamental force acceleration expression, not an equilibrium expression because we're not in equilibrium, but it's our dynamics equivalent. Now let's look at another orthogonal direction. What else can we get from our FBD? Let's look at the sum of the forces in the y. Those are going to be equal to A plus B, those two normal forces, minus 150 pounds, the full weight of the crate. This time we know ahead of time, because the crate is not sinking down into the surface and it's not flying up from it, that we do in fact have no acceleration in the y direction. So those equal, we'll just write this the dynamics way, would still equal the mass of the crate times the acceleration of the center of mass in the y direction, which just so happens in this one case to be 0. So that whole expression equals 0. So now we have an equation that relates A and B, and then embedded up here within that is going to be another relationship for A and B. So let's see if we can answer one of the questions, and that's, let's see if we can't get our ACX in this case. So let's take another little bit closer look at that expression. So we can say 35. We know that 35 pounds minus, now if we're talking about acceleration, pretty much we're looking at a situation in which the crate's moving. If the acceleration is not 0, the crate is moving, we're going to use mu k in this case. And I know that you could think of some scenarios where maybe there's an acceleration, but we're at an instant where it hasn't started moving yet. That's really only a snapshot instant, in which case we probably would have been told, at the instant before the crate starts moving. In this case, we're given a set of forces that presumably have been applied for a while, and so I think in this case it's safe to assume that the crate is moving. We don't know when the forces were applied. In that case, we would have a time-dependent scenario, but it's a fairly reasonable thing to assume that we're talking about the crate already being underway. So we're going to use mu k. I think we were given mu s and mu k, so we're going to use mu k, which is 0.15. So now we can get rid of FA plus FB. as separate variables, and we're just going to combine those and multiply them by mu k equals 150 divided by 32.2 slug times ACX 0.15, and oops, well, that was the whole point of getting rid of mu k. A plus B. So we've defined frictional force in terms of normal force in mu k, which we decided we're going to use mu k, not mu s. Now we can look back up here and say, well, I don't know what A and B are separately, but I know they sum up to 150 pounds, so I can invoke my other equation of in this case it is an equation of equilibrium, and get an expression for A plus B. So now I can solve for ACX. So I've got, basically I have 35 pounds minus 150 pounds, which is A plus B via our equation of equilibrium in the y, times mu k equals 150 divided by 32.2 slug, there's our mass, times ACX. And so if we solve this for ACX, we get 2.68 feet per second squared. Okay, so that's kind of the easy part of this problem. Now we need to use rotation to get at the rest of it. So now we need to look at, well, what's happening in terms of the sum of moments and in terms of rotation. So we can go ahead and write an expression now dividing up. Remember, we can look at motion in terms of movement, acceleration of the center of mass, and we can also look at rotation. And we can ask ourselves, okay, do we have any angular acceleration? We'd already said that crate's not sinking into the ground. It's just moving sideways. So this is the next important point we need to look at. We need to start making some assumptions about acceleration. We were able to assume ACY was 0 because the crate's not sinking into the surface. We'll also notice it's not tilting over. It's not rotating at all in the plane of motion that we're considering. So we can think about going, okay, so we can say that the sum of the moments about the center of mass of the crate would equal the moment of inertia of the crate about its center of mass in the z direction times alpha, the angular acceleration of the whole body. But we said this is 0. It's not starting to tip over. It's not rotating. Therefore, the sum of the moments about the center of mass equals 0. So we really do have a bit of a statics problem in two directions. We only have a dynamics problem when we look at the center of mass in the x direction. Center of mass is not accelerating in the y direction, so the forces sum to 0. We also know that we don't have any angular acceleration, and so the sum of the moments about the center of mass have to be 0. So that's what we can't do is take the moments about some point outside of the center of mass. So that's really the difference in how we would look at this in a statics problem. We could maybe take moment about point B. In this case, we have to decouple moments about any one point and moments about the center of mass. And so that's key to this problem in applying our sum of the moments and relating that to angular acceleration. We have to be looking at the center of mass only. So now it's just a matter of summing forces and directions to write an expression for the sum of the moments about the center of mass. So we can move up a little bit and do that. We still need our one foot. So we can start over here and go, we have effectively, we're going to look at the effect of friction and normal force due to each contact point and write it in terms of the magnitude of normal force A and B. So if we look at the rotation, the moments about the center of mass here, I'm going to draw it in a star, due to normal force B, we have a positive moment, positive coming out of the board in the k-hat direction according to our sign convention over here, due to the normal force itself acting upward, but we have a negative moment due to the frictional force at B that is a function of the normal force. So we're just going to write all of that together. So we have 1 foot positive minus, and because we're moving, we're going to use mu k. We're under mu k because we're underway. We're moving. The motion is underway. So we end up having 3.5 feet as the radius of action of our FB versus the center of mass up there, times B. And now we're gonna sum the contributions of A. So we're again going to have a negative moment due to, I'm just going to add this up, negative 1 foot. And we're again, everything at A is producing both the frictional force and the normal force itself are producing a negative moment about the center of mass. So we have minus 0.1 times 3.5 feet. So this is all negative times A. And we're going to get also our force P pushing is, of course, also going to give a negative moment. Those are negative moments are in the clockwise direction, positive are in the counterclockwise. So the only force producing a counterclockwise moment is the normal force B, not its frictional component. So we have minus 35 pounds, and that is acting at a radius of 4 feet. And that's all going to sum to 0 because alpha is 0. So we can basically go back through this, solve for, I'm not going to crank through the algebra in this case, but I can go and solve this equation and then remind myself that this is still true. So I have 2 equations and 2 unknowns, and I can solve for A and B separately, and I believe we end up with a normal force at A of being about approximately 27 pounds, and the normal force at B being approximately 123 pounds. So they sum to 150. Okay, key points. This is, first of all, this is not a statics problem. So we start with our FBD, and we start with a coordinate system. First 2 things always do on these rigid body kinetics problems. The FBD is essential. But when you finish your FBD, maybe take a step back, deep breath, and say, this is not at equilibrium. Do not dive right into starting to look at the sums of the forces and the moments equaling 0. That is a very easy thing to do automatically, especially if you really did a lot of statics problems for practice. Write sum of the forces and then MA. I alpha. always relate to the mass of the rigid body, which you may have to, use the the acceleration due to gravity. If you were given the weight in pounds, get yourself a mass in slugs or take the mass in kilos and multiply it by the appropriate acceleration. As it turns out, this problem was what we would call translational because the body wasn't rotating. Because the body wasn't rotating, we didn't end up getting into our moments of inertia or anything else. We could have treated this in a way as if we didn't need to know these separate, two reaction forces. If we just needed to know acceleration, we could have treated this as a particle at the center of mass. So translational rigid body planar motion is a lot like particle motion at the center of mass. What we did was we invoked something we knew about translation. We said, hey, I have translational motion, alpha 0. Now I basically dump myself back into the realm of statics, and I can use the sum of the moments being 0 and give myself an equation of equilibrium. But that was basically like this is a translational dynamics problem with the statics problem bolted on to get some reaction forces. Had this actually been rotating, we would have needed to calculate our moment of inertia. We would have related the sum of these forces. It wouldn't have been 0, it would have been I alpha, and we would have had another variable, and we would have needed probably some more information about the motion and invoke some kinetics, some kinematics to solve for that additional variable. So, and very essential that we use the center of mass. And that's something I'll emphasize. Although it is possible to sum the moments about another point, if you are separating your translational motion of the center of mass from some force sum, it is safest to use the sum of moments using force sums about the center of mass in general. If you don't know otherwise and it isn't too cumbersome, it's just a good default to use the center of mass because that gives you a full expression for the kinetics of a rigid body, is to have moments equaling, or the sum of the moments about the center of mass equaling the moment of inertia about the center of mass times the rigid body's angular acceleration, and then translational motion just being described by the XYZ acceleration of your mass center. There will be a few example problems we will look at with fixed rotation and general rigid body motion where we can use points other than the center of mass, but it's a good safe bet to use the center of mass for your moment calculations, generally whenever possible. So that is it. Translational problem, not a statics equilibrium problem. But we kind of got off easy that it turned out there was no rigid body rotation. So we'll introduce some bodies with some rotation in upcoming examples.